Welcome to our channel. In this session, we are going to discuss about click decision problem. Before going to discuss about click decision problem, first you need to know one important term, that is complete graph. What is a complete graph? Consider a graph G is equal to V comma E. In this graph, if there is an edge between each and every pair of vertices, then such graph is called complete graph. Suppose consider a graph with two vertices here. 1, 2. This is a complete graph. 1, 2, 3. So here, an edge between each and every pair. 1, 2, we have an edge. 1, 3, an edge. 2, 1 is edge. 2, 3 is an edge. 3, 1 is edge. 3, 2 is an edge. Edge between each and every pair. So this is a complete graph. This one is also a complete graph with 3 vertices. Suppose consider another example. 1, 2, 3, 4. Now observe, this is also a complete graph. Consider any pair of vertices, we have an edge. This is called complete graph. Now, I will give you one more example. Suppose consider this graph 1, 2, 3, 4, 5. This is a graph with 5 vertices. Now check whether this graph is complete graph or not. No, this is not a complete graph. Why? We have no edge from 1 to 5 or no edge from 2 to 5. So this graph is not a complete graph. Now, the next point is subgraph. What is a subgraph? Simply a subset of the given graph is called a subgraph. For example, in this example, multiple subgraphs are there. For example, 1, 2 is a subgraph with 2 vertices. 2, 3 is a subgraph with 2 vertices. Suppose 1, 2, 3, 4 is a subgraph with 4 vertices. 1, 2, 3 is a subgraph with 3 vertices. Multiple number of subgraphs are there. For example, consider a subgraph. Consider this subgraph. Now, this is the subgraph 1, 2, 3, 4. One subgraph. Suppose, assume this is one subgraph. Assume this is another subgraph. Like this, multiple subgraphs are there. Suppose if the subgraph is a complete graph, if the subgraph is a complete graph, then such type of complete subgraphs are called clique. Now you got the definition of clique. Clique is simply a complete subgraph. A complete subgraph. Now, for this example, multiple number of complete subgraphs, that is cliques, are possible. Suppose k is equal to 2. With 2 vertices, one clique is formed. Suppose k is equal to 3. K is equal to 4. These are the maximum. What are the possible things? With 2 vertices, 3 vertices, and 4 vertices. Anyway, with 5 vertices, this is not a complete graph. So, next thing is, once you understand what is a clique, the next to the most important is size of clique. What is the size of clique? So, for this k is equal to 2. A subgraph consists of 2 vertices. So, size is equal to 2. K is equal to 3. The size of clique is equal to 3. K is equal to 4. The size of clique is equal to 4. Now, what is the answer? Simply, size of clique is equal to simply the maximum number of vertices. The maximum number of vertices is called size of clique. Now, what is the clique size? Among all the subgraphs for k is equal to 4, the subgraph is formed with maximum number of vertices. Clear? Now, first what we discussed, what is a complete graph? From that complete graph, how do we generate a subgraph such that the subgraph is also complete graph? Such type of complete subgraphs are called clique. Now, what is the concept? Clique decision problem. Once you understand the definition of clique, the next definition is what is mean by decision problem. Decision means for any problem, if the solution is either yes or no, such problems are called decision problem. Suppose, see this one, 1, 2, 3. 1, 2, 3. Suppose this subgraph is a complete graph? Yes or no? Yes. Suppose 1, 2, 3, 4. Is this subgraph is a complete graph or not? Yes or no? Answer is yes. Suppose 1, 2, 3, 4, 5 is a complete graph? Yes or no? No. That is, for any problem, if the solution is either yes or no, such problems are called decision problem. Next, optimization problem. What is the need of optimization? Remember, for any problem, multiple solutions are there. For example, for this, multiple subgraphs are there. One subgraph of clique size 2, clique size 3, clique size 4. Which one is optimal? So the maximum number of vertices k is equal to 4. Now you got it? Optimization problem in the sense you need to find out the maximum size of clique. You need to find out the maximum size of clique. This is called optimization problem. Till now, what we understand? What is a clique decision problem? Now, what is the clique decision problem? For a given graph, we need to identify a complete subgraph, and at the same time, among the complete subgraph, find out the maximum clique. Find out the maximum sized clique. Now, what is the question actually? All these are comes under decidability, undecidability problems. Our aim is to prove CDP, clique decision problem is NP hard. This is our given problem. Our problem is we need to prove that clique decision problem is NP hard problem. The question is, how do we prove a problem is NP hard problem or not? We already discussed. Directly it is not possible. So for your understanding, I explain one more time. Assume I have one problem, L1 is there. Assume already L1 is NP hard problem. That means I take already known NP hard problem. For this NP hard problem L1, I am taking one example. Now, consider another problem L2. I don't know whether L2 is NP hard or not. My aim is to prove L2 is NP hard. For this L2 also I am taking one example. Okay. L1 is already known NP hard problem. For that I am taking one example. L2 means my requirement to prove. I taking one example. Now, the example of already known NP hard problem is polynomially reduced to. An example of this problem. If the polynomially reducibility is possible, then we say that L2 is also NP-hard. This is the concept of proving a problem is NP-hard. Now coming to her question, here what is L2? Simply our CDP is L2. That is your aim is you need to prove clique decision problem is L2. So to prove this one, you need to know any known NP hard problem. So I already known that SAT. What is SAT? Satisfiability problem. Satisfiability problem is already NP hard. Now, what is your aim? You need to take one example of satisfiability problem and convert into an example of CDP. If the conversion is possible, then simply we say that CDP is NP hard. Now, consider an example of satisfiability problem with three variables. So, x1 or x2 and x1 bar or x2 bar and x1 or x3. So here I am taking three clauses. Suppose assume C1, clause 1, clause 2, class 3. This is satisfiability problem example. Now clique decision problem. How the example of clique decision is available? Clique problems is in the form of graph. So you need to convert this F into graph format. What the graph consists of? Graph consists of vertices and edges. How do you design a vertex? So the vertices are written in this structure. Remember the structure AI, comma I, such that AI belongs to CI. What is the meaning? It's very easy to understand. I specifies the clause number. AI specifies each and every variable. That means how many number of vertices you have? 1, 2, 3, 4, 5, 6. Total 6 vertices. So first I will write down all the 6 vertices. How do you write? For example, vertex 1, the structure is x1. x1 belongs to class 1. So here you need to write x1 comma class 1. This is one vertex. Now draw one more vertex. Here x2, A specify x2 belongs to which class? Class 1. So x2 comma class 1. Clear? Now for the second class, x1 bar comma 2. So for this, I will written like this. x1 bar, comma 2. Now one more vertex. x2 bar, comma 2. x2 bar, comma 2. So second class is completed. Now coming to third class, x1, 3. Third class is x1 class 3. Now x3 class 3. Now everyone clear with how do we write the vertices? This is the way writing the vertices. How many literals are there? Each one is considered as a vertex along with the class number. Now vertices are clear. How do we draw an edge? Some rules are there. The first one is there is no edge between the vertices of same class. There is no edge between the vertices of same class. That means, see here, there is no edge between x1 to x2. There is no edge between x1 bar to x2 bar. No edge between x1 to x3. Clear? So, for the same class letters, no edge. Now, there is no edge between the vertex and its inverse. Even though that is in a separate class, edge is not possible to write. So here see this one x1. What is the inverse x1 bar? Even though it belongs to class 2, it is not possible to write an edge. It is not possible to write an edge. So based on that constraints, write down the remaining edges. First, x1 to x1 bar edge is not present. Now x1 to x2 edge is present. Yes, I'll write edge is present. Now x1 to x1, is it possible or not possible? Possible. Why? This belongs to class 1, this belongs to class 3. Different classes, edge is possible. X1 to x3 edge is possible. Now coming to x2, this is x2, this is x1 bar, no problem, edge is possible. X2 and X2 bar inverse, not possible. X2 and X1, here the edge is possible. X2 and X3 edge is possible. Now, X1 bar to X1, inverse not possible. Anyway, X1 bar to this one, this is an undirected graph, already edge is drawn. X1 bar to X2 bar, same class, not possible. X1 bar to X1, no, why? Because these are inverse. Now x1 bar to x3 edge is possible. Now coming to x2 bar to x1 completed. X2 bar to x2 not possible. X2 bar to x1 is possible. X2 bar to x3 that is possible. Now x1. So already x1 to this one completed, x1 to x2 completed, this inverse is not possible, x1 to x2 bar completed. Similarly, x3. So from x3 also all the edges are completed. Now clear? So graph is constructed successfully. Now from this graph, you need to identify a subgraph. Take any subgraph such that the subgraph is a complete graph. For example, not only this, you can take any subgraph. Suppose this is one subgraph I consider, or else suppose you will consider one more triangle. See this one? Like this, you can take any subgraph. For example, I will take one subgraph. So this black color subgraph. In this subgraph, what are the values of x1, x2, x3? So for this subgraph, x1 bar is considered. So x1 value 0, x2 there is no inverse, x2 value is 1, x3 there is no inverse. For these values x1, x2, x3. Now go back to here, apply the values x1. I will write down one more time. What is f? F is equal to x1 or x2 and x1 bar or x2 bar and x1 or x3. What are the values? x1 is equal to 0, x2 is equal to 1, x3 is equal to 1. Now got it? From the graph, I am taken a complete subgraph. What is the complete subgraph? Clique. I am taken a clique. For that clique, these are the values. Now, I am substituting all these values in this equation. 0 or 1. And 0 bar means 1 or 1 bar means 0. And 0 or 1. So, 1 and 1 and 1, that is 1. 1 in the sense the answer is equal to true. 1 in the sense the answer is equal to true. Now, what is the meaning of this one? Here, we are getting a clique. For that clique, Here for the satisfiability problem also, the result is true. For satisfiability problem also, the result is true. That means we are polynomially convert this satisfiability problem into clique decision problem. That means clique decision problem is also NP hard problem. Clear? This is the concept of clique decision problem. Read and understand. How do you solve? First, you need to understand what is a complete graph. Now, what is a subgraph? Next, what is the complete subgraph? That is called clique. Now, what is the meaning of decision problem and optimization problem? What is your requirement? So, to resolve your requirement, what you are taking? An example of satisfiability problem that is converted into a graph by using these notations. Take any subgraph and for those values, if it returns true, in the sense the satisfiability is successfully converted into clique decision problem, then such that CDP is NP hard. That is the end of session. Thank you.